Okay, so the plan today is to talk about Compton's effect. Remember when we started talking about it and we said that when light interacts with matter, three things happen. The first of them was photoelectric effect. The second was pair production. The third is Compton's effect, right? And so we are now going to do Compton's effect today, okay? So what is Compton's effect? So let's start here. People in the early 20th century were studying light incident on different things. So they shone light of different colors, of different wavelengths onto metal surfaces, onto other surfaces, and they saw what light was doing. We thought of light as rays or as waves. And so these were things that were developed and people understood those at that time. So what did people understand? In 1900s, common understanding. Wavelength of scattered X-rays should be equal to initial wavelength. When X-rays are made incident on matter. When you shine a light onto matter, the wavelength coming out of the light should equal the wavelength that was going in. So if you shone a red light onto something, you should expect a red light to come out. If you shone a green light to something, you expect the green light to come out, right? If you shone a blue light to something, what should you expect? A blue light to come out, right? That was the common understanding. However, when they actually did these experiments, they found so many early experiments in the 20th century, like the beginning of 20th century, like 1900s to like 1920s to 30s to 40s, what they were seeing is the scattered lambda was longer than initial lambda, which meant that the energy of the scattered lambda was lower than the energy of the initial. So extreme case, a blue going in was turning into a red light coming out. Like, of course, that's an extreme scenario, right? That won't happen. But the wavelength that was going in was different than the wavelength that was coming out. So they realized there was more to light than just the light being called a wave. That was number one. There is more going on here than when light is treated as just a wave. Classical theory of electromagnetic waves, which was also called the Thomson scattering, does not explain this phenomenon. And classical theory of electromagnetic waves, which is also called the Thomson scattering, cannot explain these shifts in wavelengths. Another thing that was going on was that the classical theory predicted that for accelerated particles, these two effects will happen. So classical theory also predicted two things. Light of sufficient intensities for the E field to accelerate a charged particle to relativistic speeds will cause, number one, radiation, pressure, recoil, and number two, associated Doppler shift of scattered light. Do we understand what Doppler shift is? Sort of? No? We've not heard that word before? Okay, so a Doppler shift is actually, you know, like how the ambulances pass you by and it seems like their pitch is going up, 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 and then they go down, down, down. I may actually have, oh, here we go. Like this. If there was a source that was just emitting normally, and you're just listening to it, listen for this, guys. Do you recognize that? When sound is coming and then sound is going away from you, that's called the Doppler's effect. The actual frequency change that is happening, where you feel like that there is a sound that's coming towards you versus going away from you, what is happening here is this. When a source of sound or light moves, the waves that it's emitting in the at the front bunch up, whereas the waves that are at the back become larger. So the wavelength actually changes for a moving source. So when the observer moves towards the source versus when the source moves towards the observer that is standing. In both cases, you will see what is called a Doppler's effect. So what do you observe here in this picture? This side, when it's coming towards you, these are bunched up. But when it's going away from you, these are far away. So the bunching up will cause an increase in frequency. Whereas when it's going away from you, it will cause a decrease in frequency. There is a very good reason for it. When source and observer move towards each other, the distance between them decreases. However, the speed cannot change. So something else has to change. Remember this formula, lambda f? If lambda is becoming smaller, then frequency has to become larger in order to compensate so the c doesn't change. And there are these formulas. But for us, doesn't matter, but just to explain Doppler's effect, I need to show you these. And that happens for all waves. So this is an explanation for sound waves, but we also have the same phenomenon when we talk about light. It's all connected. Yeah. Isn't that cool?
Okay.
Okay, now coming back to Doppler's effect. So we would see this. However, this effect would be negligible at low intensity of incoming light. Did we, in photoelectric effect, say that it does not depend on the intensity of light? Remember, we increased the intensity, then we decreased the intensity, and nothing was happening. That's exactly what Compton was observing in his experiments. He was like, wait, what's going on? Classical theory says that if my intensity is small enough, I shouldn't be seeing anything. But he observed, kept seeing scattering even at very low intensities.
First what's that? Radiation pressure recoil?
Yeah. It's basically the recoil that will happen because of radiation actually being emitted. And that's what they were seeing, so that was not a problem. It was the fact that they were observing all of these things at even low intensity. classical physics predict that you need high enough intensities for this to happen. But all they were seeing was that these effects are happening all the time, even at very, very low temperature, very, very low intensity. And the only thing that it seemed to change is frequency. So frequency is the thing that's changing everything. Remember in photoelectric effect, we looked at it, right? We kept increasing the frequency and suddenly it started, and now it doesn't matter how intense the thing is, it will still ejecting. That's exactly what Compton was seeing at least 15 years after Einstein had predicted that to happen. So he actually convinced other physicists by his experimentation that instead of thinking about light as a wave, we have to think about light as a particle, and Einstein was right. Because E, the energy of the light photon, is proportional to the frequency, and E equals hf. Exactly how Einstein had predicted it. Okay, so shall we write that down? So he, through his experiments, convinced physicists that light can be thought of as a stream of particles, quanta, or photons with energies proportional to F. And E equals HF, where H was the Planck's constant. So when we study these things, we always study them in terms of the scientific merit. But think about it. Einstein said well, not Einstein. Before him, people were doing experimentations that led to photoelectric effect, right? And when was that year? 1906. How old were you in 2006? How old are you now in 2022? Imagine when you were 5 years old, somebody saying something and you coming along now in 2022 doing experiments that completely different experiments that proved the exact same thing. That the only way you could explain what you were seeing experimentally was going back 20 years ago, looking at something that somebody else was doing. That is so fascinating. At least in my head, it's like, whoa, where was I in 2006? Imagine. He also proved that the only way to explain it is by considering light as particles that carry energy with them, and the amount of energy that they carry with them depends on their color, basically the frequency, right? So red light has more energy or blue light has more? Blue light has more, and blue light has shorter wavelength, higher frequency.